Hello everyone, my name is Chicago Patterson, and in this tutorial I'll be focusing on atoms, and in particular I'll be going over quantization, wave-particle duality, as well as orbitals and periodic table trends. Starting with the topic of quantization, why is quantum theory and quantization important? Well, quantum theory and quantization are important because there are situations in which classical physics is unable to describe certain phenomena accurately. So what exactly is quantum theory and quantization? Quantum theory is a theoretical basis that is used to explain the behavior of matter and energy on a very small scale. Quantization is the idea that a certain physical quantity can only have certain values. An example would be how a non-negative whole number can describe how many atoms are in a certain area. So some examples of when quantum theory is needed and when classical physics breaks down are black-body radiation, the photoelectric effect, Schrodinger's wave equation, and the uncertainty principle. So what exactly is black-body radiation? Well, all objects above absolute zero emit radiation, but a black body is an object that can absorb and emit all the different frequencies of light. The radiation that black body objects emit varies based off of temperature. To be specific, the radiation of a black body radiator is created from the thermal activity of the material. So what is the ultraviolet catastrophe? The ultraviolet catastrophe, which is also known as the Rayleigh-Jeans catastrophe, was considered a catastrophe because at shorter wavelengths, the Rayleigh-Jeans equation calculated the spectral radiance to be a lot larger than it should be. The spectral radiance that was calculated with the Rayleigh-Jeans equation was so high that it would cause all matter to instantly radiate all of its energy until the system almost reaches absolute zero, which is why it was considered a catastrophe and which indicated that a new model must be made. So how is quantum theory able to explain the black body spectrum and avoid the ultraviolet catastrophe of classical theory, and how does it work? So Max Planck, who is one of the founding fathers of quantum theory, was able to explain the black body spectrum by proposing that the amount of energy that a light wave can exchange with matter was not continuous but discrete. Planck suggested that the energy was quantized, and he modified the Rayleigh-Jeans equation. Max Planck's discovery that energy was quantized and not continuous also helped to solve the ultraviolet catastrophe by discovering a mathematical trick to calculate the spectral radiance. By finding a trick to accurately describe and calculate the ultraviolet waves emitted from a black body, the ultraviolet catastrophe had ended. Einstein later came up with a physical explanation for Planck's so-called mathematical trick, and concluded that Planck's trick was not just a trick, but it was an accurate method. As you can see on the bottom of the slide, there is a formula for calculating the spectral radiance, and this is one of the forms of Planck's equation for the spectrum of black body radiation, and H represents Planck's constant, C represents the speed of light, and K represents Boltzmann's constant. As you can see from the photo on the left, that is a photo depicting black body spectrum, and you can see that classical theory was pretty off at describing UV radiation, but it was fairly accurate for infrared. And the photo on the right, that depicts a black body radiator, and it's showing that it can emit all kinds of light. So what are some real-life applications of quantum theory? Well, toasters make use of it, computers and phones, microscopy, which also makes use of wave-particle duality, GPSs, quantum clocks, lasers, MRI scans, and artificial intelligence, as well as plenty more. So moving on to the topic of wave-particle duality. Wave-particle duality expresses the fact that lighter matter can be described as either a particle or a wave, and that everything exhibits either wave and or particle behavior, and in some cases can do so simultaneously. So how does wave-particle duality work? Well, as I had mentioned, light and matter exhibit properties of both wave and particles. So, how do the particle properties of photons compare to the wave properties of electrons? Well, the biggest difference between the properties of photons and electrons is that photons have no mass, no electric charge, a spin of 1, and they only exist as a particle in motion. Both electrons and photons have momentum and energy, even though photons don't have mass. Electrons can collide with particles and can be diffracted just like light, and the wave properties of electrons are easier to demonstrate through experiments compared to other particles such as neutrons and protons. So an interesting property of electrons is that they all have equal mass and charge. So then, what other particles have been used to demonstrate this? Well, some other particles that have been used to demonstrate wave-particle duality include neutrons and protons. Now moving on to the Davison-Germer experiment. So this experiment demonstrates wave properties of electrons. So this experiment confirmed the de Broglie hypothesis, which proposed that all matter exhibits wave-like properties. And as you can see on the graph to the right, the intensity of the scattered electrons graphed against accelerating voltage illustrates the wave-like behavior of electrons. Now this depicts light acting like a wave and a particle simultaneously, and light just acting like a particle. The photo on the left was the first photograph that was taken that demonstrates light as both a particle and a wave simultaneously. So scientists were able to capture this photograph by shooting a stream of electrons close to a nanowire and using them to capture a photo of the standing wave of light. As electrons hit the light on the nanowire, the electrons either sped up or slowed down. This change in speed of these electrons corresponds to the change in energy which is transferred between the photons and electrons. By using an ultra-fast microscope, they were able to visualize the standing wave of a photon, and this photo was just taken within the past few years. According to researchers, this may help in the research towards building super-fast quantum computers due to our ability to observe light in such a manner. In the 1800s, Thomas Young claimed that light has properties of a wave. Young conducted an experiment in which he created a double-slit interferometer to demonstrate what happens when two waves interact with each other. This photo demonstrates how waves of light can add on to each other to make a wave of larger amplitude or to cancel each other out. This photo depicts what happens to waves of light going through a slit. Now moving on to the last topic of this tutorial, orbitals and periodic table trends. So as you probably know, ionization energy for the most part increases as you go up and to the right of the periodic table. This is due to the atomic radii decreasing in size as you go up and to the right of the periodic table, which means that the attraction between negative and positively charged particles is stronger as the atomic radii decreases. This causes the amount of energy to remove the loosest electron to be larger as you go up and to the right of the periodic table. Another explanation for the ionization energy trend for columns is that when you move down the column, there are more valence shells, so that the valence electrons are further from the nucleus, which means there's a weaker attraction between the nucleus and the outermost electron, which makes it easier to remove an electron. So the ionization energy decreases as you go down a column. For the most part, these trends are accurate. However, there are some exceptions, such as boron and oxygen. The reason for these exceptions in ionization energy trends is because of the electron configuration of the atoms. For example, the electron configuration for oxygen has one electron too many to be stable, compared to nitrogen, which has a stable electron configuration, so the ionization energy for oxygen is less than that of nitrogen, which goes against the trend. From these trends, you can probably determine that the noble gases have larger ionization energies than the other families. This is because they are already in a stable configuration. So it's intuitive that it would take the most energy to remove an electron from a noble gas. As you can see on the bottom of the screen, there is a photo that depicts the periodic trends in first ionization energy in 3D. As you can see on the photo on the left, this photo depicts the ionization energy trend of the periodic table, which I had described. And then on the right depicts the exceptions to the trend. So you can see that there are quite a few exceptions. Now moving on to some ionization energy sample problems in which we determine which atom has a higher ionization energy. So firstly, magnesium or silicon. So if you look on the periodic table, silicon is to the right of magnesium, so that should mean that silicon has a higher ionization energy. Then moving on to the second one, which atom has a higher ionization energy, chlorine or iodine. So chlorine is higher than iodine on the periodic table, so that should mean that chlorine has a higher ionization energy. And moving on to the last one, nitrogen or aluminum. So as you can see, nitrogen is to the right and above aluminum, so that should mean, according to our periodic table trends, that nitrogen has a higher ionization energy. Thank you for listening to my tutorial. I hope you learned something, and here are my references.